Now moving to like work and like research environment, like what do you value the most regarding like training students and like you're training new students? As you said, like just a moment ago about like who is a physics PhD, you did say like having this sort of independence is an important quality you try to develop in your students. But is there other things you would like to add to that?
Yeah, I would say taking ownership, even if they are not independent to begin with. Taking ownership, meaning um, I would like them to engage with me in discussions to understand the big picture of the problem. Because unless they are invested in the problem, they won't be able to put their heart into it and work on it. So, trying to have a lot of dialogue, reading the literature on their own, scouring, they know more ways of accessing Google Chat and Chat GPT and all that. So, using all the available resources to see what's going on, to come up with their own questions. Um, that's something taking initiative, both of these things.
Okay. All right. So now moving to like
Another thing I would
yeah, go
say
ahead.
is trying to understand the result they get from multiple angles. So let's say they do some numerics, kind of complementing that with analytical methods. So that's something I value a lot in my research is multiple methods. You None of them, these are very hard problems. Unless you solve it exactly, you will have some kind of an approximate solution. So each approximate method has its own insights. So insight is what we are after. So you get a result, but you want to view it from many angles. Some rules, you know, thermodynamics, what kinds of constraints does that put? Then using, even if it's mean field, getting that result tells you the difference between that and the full numerical result must be a consequence of fluctuations. What kind of fluctuations? And so that kind of logical step by step understanding, I think, is very important. And the second thing I think that is very important is working hard to explain your results. For example, when you give a talk, people try to present it, but I'll show you later, I have a sequence of pictures of a bull that Picasso made. It starts out with an actual bull that he has sketched. Then he simplifies it. And in the original, he has 19 sketches. The last one is a minimal sketch of the bull. But you can look at it and still see the beauty of the bull in that. And it's not a spherical cow.
Okay.
You can see it's a bull.
Okay.
But it's much simpler than the original. So that's what I mean. You have a result. Now you have to etch it to remove all the inessential things, to distill the essence of that and be able to talk of the key result. And in any, and I think this practice, I think, is very hard for students. I see even in their final thesis defense, there is a lot of material. And no matter how much I work with them to tell them to throw things away and to distill that gem out of it, it's very hard. And I think a lot of my own career later on has been spent on how to say the most difficult concepts in the simplest possible ways, either by drawing. That's why I don't like a lot of complicated color plots. I like to sketch things. I'm a big believer in blackboard talks. The communication is so much deeper, so much more information is communicated. I like to give all my lectures by writing on the board. I don't like PowerPoint talks. All of that, I think it goes to my desire to communicate with simplicity and with depth.
Okay, I see that. I actually also like struggle with that a bit, so I think it's
I think it's a
uniform.
continued struggle. It
Yeah,
takes decades. It has
takes
taken me a
time.
long time, yes.
Yeah,
And you try to observe people who do it well, and then you make mental notes about their way of describing something. And then you learn from them and you make little mental notes, or you keep that in mind when you have to do it. And that's where I do value teaching, because it gives, you may say, oh, I know this subject, but it doesn't matter. It could be, teaching undergrads or teaching even non-physics students. I have some of my best friends that I have are these medical students who took our basic physics courses. They are people who tell you they don't like physics. And then when that happens, that's a challenge, right? They don't like physics. How do you make physics interesting for them? So you have to come at it from their angle. That's why physics is a lot about communication and connection. So you have to not just stick with my way of doing things. You have to understand the other person and try to connect with them and try to tell the story in a way they will understand.
That's an important part, especially for science communication.
Yeah.
Kind of things. So, since we are talking about like challenges to graduate students, I think, especially for like OSU students, one of the main challenges that they face early on in the PhD is the candidacy exam. So, what is like in your opinion, like what is the goal of the candidacy exam, and like or like what is your philosophy of the candidacy exam? Like, what do you look for in a students going through a candidacy exam, for example?
I think basically what I look for is mastery of the core courses. So the candidacy exam is basically structured around a specific paper. So it's kind of trying to see it's a midway point between core courses and research. So it's a very interesting format where you kind of throw at the student, literally, an incomprehensible paper. And it's very daunting because you read the abstract, you have no idea. You start reading, you have no idea. And now you have to present it. And it's very daunting. But it's kind of a beginning of what research will look like. So this is where you need to have the test that you have solidly understood the fundamentals becomes very important. So you learn to see, okay, there is this lot of things being talked about. What are the main concepts left in the paper? So you look to the title, the figures. What is a figure trying to say? Even without reading the paper, just reading the caption, can you kind of distill what the figure is trying to say? Can you connect that with something you have learned about in your courses? Maybe it's showing some specific heat of something, of some material. Now you connect with entropy, specific heat of an electron gas or some, magnet, and you try to see, does it look anything like that? So that is how you start to find puzzles in your later research, is by having an anchor point, seeing something new, and trying to see how does it deviate from the anchor point. And then you'll start to ask, do I understand this? What is the puzzle? And the candidacy goes on from there.
I see. So, okay, I guess this covers also this part like pretty well.
I think another important thing I feel in my research has been, and that's what this brings out, is how to look at data.
Like figures?
Like figures. Like, you see some data plotted. Okay, how do you look at it? First of all, what is the y-axis and the x-axis? Then there is units. What is the scale? How much is the temperature varying? How much is the entropy varying? what are the maximum entropy it could have or specific heat, what are the features, are there some peaks, but really dimensional analysis and scales can take you very far. So just understanding that, if there's a peak at some temperature, 10 Kelvin, okay, what does 10 Kelvin mean? 10 Kelvin is basically 1 milli-electron volt. So something should be happening at 1 milli-electron energy scale. Is there something in the spectrum? So like this, you start to connect what you read in a course in a very linear way. You start to connect different parts of it.
And that's really important.
Yeah.
That's really important for a physics PhD as well.
Yeah.
So I think like as a concluding question, since we did talk about part of that, like how do you approach balancing like the quality of the research with like the pressure to publish, since this is I think one can be one struggle for like students that they really enjoy the problem but they also know that they have to work on it like fast in a fast pace a little bit so that they can actually be the first to do that, or have you faced like any problems with this with your students or like in your group before?
Yeah. I think you have to balance. Like it depends on the kind of field. Like I have often worked in different kinds. So for example, when I was working on high temperature superconductors, it had a huge number of scientists working on that topic. So at that point, when you get a nugget of a result, you try to publish it because you don't want to get scooped. But that's not the kind of problem I always worked on. So high temperature superconductivity was like it's like a problem which just drew you in. But usually for example, when I went to India, I knew I couldn't be competing with people in the US. I had to work on a very different kind of problem. And so you have to be strategic, right? You want to work on something deep, something important, but at the same time, you don't want to get scooped when you just have some important result and you were slow writing it up because you wanted to do many things. So it's a little judgment call, and it depends on two things: the kind of problem and the environment you are in. So I described to you one kind, like the high TC superconductivity. When I went to India, I was like, this will need a different strategy because I can't compete with what is happening in the West. And actually, just a sequence of questions brought up a problem that we literally discovered and developed for the first time in India. And I'll tell you briefly about the problem. So high temperature superconductors have Cooper pairs, but the question is, what is the wave function of the Cooper pair? If this electron is up, is the down electron in an S wave state, like uniform probability around it, or is it in some like P wave or D wave, some other state? And there's a well-known theorem I should say, but it's kind of not a theorem, but it's a weak disorder result, that if you have disorder, it does not affect S-wave superconductivity. Because, you have a uniform probability, so your electron gets scattered from one momentum to another, and if it's uniform, it doesn't matter very much. If it's D-wave, which was the other prevalent view, then it's very sensitive to disorder. So in the high temperature superconducting systems, it was believed that these were D-wave superconductors, but that didn't gel with the fact that they were quite disordered. So it was a big puzzle. What how was this going to fit together? D wave, but also unaffected by disorder. So I was like, let me try to work on this problem, but from another angle. I was taking my first graduate student in Tata Institute in Bombay, and the problem I gave him was to look at S-wave superconductors with disorder. And I said, this problem is well known. It's known as Anderson's theorem. So it's all well established that nothing should happen to superconductivity when you put disorder in it. So why don't we just repeat and just reproduce this answer? We are under no pressure. I'm sitting in India, near the sea, beautiful place, enjoying a different kind of life. We just repeat. I'm not under pressure. So it was a different environment. So he repeats this, and there was crucial assumption people had made in calling it Anderson's theorem, and that was the assumption that disorder is weak. And I'm like, why weak? Let's crank it up, make it large. And we had numerical methods that people hadn't used before, and we discovered some new things there. A superconductor to insulator transition in which the insulator still had Cooper pairs. So it's a completely new insulator. I told you about, in this short discussion, I've told you about a band insulator in silicon. We talked about Mott insulator, and this is now a new insulator where Cooper pairs are paired up, but they are not superconducting. So this was our discovery for S-wave superconductors in disorder. Nobody had seen this before. It was our prediction, and we wrote it up, quietly. We were not in any hurry. We wrote a PRL and we wrote a PRB long article, and it was almost, nobody would believe me when I would give, this is the other fun part about physics. You go to give a talk and people are so disbelieving. They're like, oh, this cannot happen. And now I look back at those very joyful, exchanges, not so joyful at that time. But you have done your calculation. You can explain what are the framework in which this has been derived, and that's the result. And rather amazingly, a decade later, 10 years later, not 10, maybe 8 years later, because after 10 years I was at OSU, but 8 years later, I went to ICTP, which is the Institute of Theoretical Physics in Trieste. It played a big role in bridging between, Eastern air science and the West by giving us a place where we could travel to. And, because money is in short supply, and, it's hard to come to the West with all these constraints. So I went to ICTP Trieste, where I presented these, where an experimentalist was presenting their data, and they were showing the theory side by side, showing how the experiment exactly agreed with the predictions of the theory. So, which was fascinating. So, and it's a very clear prediction. In a superconductor, a gap opens up. Everyone thinks when you put in disorder, the gap will kind of fill up. Our prediction was the gap never fills up, even when it becomes insulating, but some other energy scale, the superfluid stiffness, becomes zero, but the gap doesn't close. And this exact experiment was seen by STM. And I was fascinated to see the theory being shown side by side. Yeah. So, I have almost never been driven by, like, of course, you have to be a little astute, and you have to know that in spin liquids, if it's a hot field, you should publish quickly. That is also true. But generally, try to keep your eye on the science, and, don't, I would say, in the haste of publishing, don't lose out on some nugget. Yeah. I want to say one last thing. I started, beginning in physics was with the two-slit experiment. And that thread has taken me to entanglement. And now the very latest new thing I'm doing is to try to understand how measurement, quantum measurement, happens. You know, we all know when I teach quantum mechanics to my undergrads, I tell them about a superposition state, let's say a qubit, which is a superposition of up and down. When you measure, it projects into one of your computational states, either up or down. How that happens, it's a rule, that's what we are told. It was very dissatisfying for me when I learned it, when I teach it, and now finally I'm getting to this question with one of my graduate students by going through the route of what we call weak measurements. So we don't do a projective measurement, which projects it into one of these computational states, but we add another qubit, which is weakly coupled to the system, the ancilla, we call it an ancilla. On this ancilla, we do projective measurements because there's no way around that. Quantum mechanics is this way. This is how it works. But the ancilla is weakly coupled to the system. And the question is, how do you break down the projective measurement through a sequence of weak measurements? So this is kind of going to be, I think it'll be quite, I will at least feel very satisfied when I come to the point where I can hopefully say at some point I really understand this process. Yeah.
Yeah, that would be really interesting to observe. And yeah, I guess with that, we actually covered most of the things. I would say maybe like what advice do you have for graduate students regarding like balancing graduate school with their maybe like life or like health?
Oh, no, that's very important.
So,
That's very important. That's something I would say I neglected. I neglected. Hmm.
how would you change it?
Yeah, I would change it based on what I see in my children. They are much more aware. For me, food was food, what tasted good, but they are much more aware of all the components that go into making food. Much more aware of, like I love to play badminton. I didn't think much beyond, like this was fun, but and then, when work became, there was a lot of pressure, I would give up on that. But they have taught me that there are ways you can very efficiently do something you like, and that's up to you, what you like. I like to run. So very late in my career, I started running. Not much, but just even like 5Ks. And then exercise and weightlifting and balancing, but making a schedule. And I found doing it early in the morning before any other pressures take your day away, but just sticking to it. To the point where when you're not in the habit of doing it, I have seen people who love doing it just naturally find the time. When you haven't done it, it always falls through the cracks. So it's come to a point where I kind of prioritize it even a little higher than my work. Like in the morning, I must get it done. Otherwise, I know I will have no health left to do the work. So literally, I would say, prioritize that over and above everything, because that health will then help you do the work you want to do.
Okay. So that's how you would achieve.
That's how I would say it now, but that was absolutely not my perspective going in.
That's a great advice that I also try to implement.
Yes, and I have to say I've learned that from seeing the younger people. I would say another thing is just take breaks and take them without guilt. I know I would take breaks and then I would keep telling myself, and I should be working. Terrible state of mind to be in. When you're out in the woods, High Banks or Sharon Woods, in the middle of the forest, just take in the forest, enjoy the flowers, the hikes and nature or whatever you like to do, and then just disengage. That's another thing I would do differently.
Noted. So thank you so much for your time, Dr. Nandini. This was
Yeah,
really
thank you so much.
amazing.
It was really wonderful to talk to you, Ayman. And
Yeah,
we should definitely have a chat sometime and you should tell me your story.
I'm happy to.